everyone, welcome back. Uh, Last time we began talking about anti-differentiation, which, as mentioned, um, was the undoing of differentiating. So we spoke about this symbol called the integral, and we saw that whenever we wrote the symbol, the integral of f of x dx, that is equal to capital F of x, where capital F of x is the antiderivative of f of x. So we call this the antiderivative. Now, just for a quick example, just to refresh our memories, if let's say you're given the function f of x is equal to 2x, and somebody asks you to find the antiderivative of f of x dx, what they mean is to find the integral of 2x dx. And what this basically boils down to is basically finding a function capital F of x whose derivative, so f prime of x, so we don't know what the function is right now, but we would want to know what function f of x has to be so that its derivative is equal to 2x. And 2x is little f of x. Now, last time I introduced a rule on how to do this, which I call the reverse power rule, that said the following: if you have something of the form the integral of x to the p dx, then that is equal to x to the p plus 1 divided by p plus 1. So if we go back up here to this problem, we have the integral of 2x dx. And much like with the derivative, we had the constant multiple rule that allowed us to pull out this 2 to the outside of the integral sign. So we could write it as 2 times the integral of x dx. And now we have something of the form x to the p dx. And we saw from last time that this is the same thing as 2 times x to the 1, because it's power 1, plus 1, divided by 1 plus 1, plus c. Because remember that this indefinite integral is not unique. There are an infinite amount of functions that will actually give us the same antiderivative. The same antiderivative. There are an infinite amount of antiderivatives that will give us the same derivative here. So anyway, we get 2 times x to the 2 over 2, which is equal to x squared plus c. So we can see that if c is any constant, anytime we take the derivative, we're going to get 2x dx. So that is what we did last time. In this lecture, we're going to be talking a little bit about area. Now, this is a problem that we introduced earlier in the term when we first began talking about what calculus is. I told you guys that two of the most important things that we'll look in this class was the problem of the tangent line and the problem of area under a curve. Well, we saw already how the derivative can be used to find the slope of the tangent line at a particular point in a function. And once you have the slope of the tangent line, then if you have any other point on the graph, then you could find the equation of the tangent line passing through a point on the graph. Well, now we move into the other problem that I mentioned earlier in the term, and that is the problem of finding area under a curve. We will see that finding the area under a curve is very much related to this problem of the antiderivative. So this is why we're introducing it now. And then when we talk about the so-called fundamental theorem of calculus, you will see exactly how closely related area is to the integral or the antiderivative. Now, before we could run, we actually have to be able to walk, and before we could walk, we have to be able to crawl. So let's crawl our way into the fundamental theorem of calculus. I will first begin by defining some notation. This notation is called sigma notation, and it is called this because of the Greek letter sigma, which is written as this. So this is, let me see if I can do it better. So this right here is the uppercase letter sigma. So this is an uppercase Greek letter called sigma. That's what that is. Now, what we're going to use for this section is called sigma notation. Sigma notation is a neat way and a very concise way of writing sums, either finite sums or infinite sums. So sigma notation, we have that the sum of n terms, let's say a1, a2, a3, all the way up to an, is written as in the following way. It's written as the sum, so whenever you see the sigma notation, you immediately think of a sum. So that's why I'm saying sum. The sum of from I equals 1 to n of ai, which is equal to a1 plus a2 plus a3 plus all the way up to an. So here we are writing the sum in this fashion, which is a very concise way of writing this infinite piece. Now here the I, that I is called the index of summation. Sometimes you may see k used as the index, so it's very common to see I, k, n. It's also another index that gets used a lot. So this is the index of summation. AI is the ith term of the sum. So for example, if you say A3, that will be the third term of the sum. You know, if you say 87, that will be the 87th term of the sum. That's why it's called the ith term, because when you get to really large numbers, you'll be like the 247th term of the sum, and so on. And the upper and lower bounds of the sum are n and 1 respectively. So this n that you see up here, this is the upper bound, and this 1 is the lower bound. Now, what do I mean by upper and lower bound? That is the max. N is the maximum value that the sum achieves, and the 1 is, for this case, the lowest value that the sum achieves. So let's do some examples about sigma summation and adding things in this form. They're not particularly difficult to do, at least not at this level. So let's say somebody came up to you and gave you the sum of I equals 1 to 6 of I. Well, what does this mean? This means to sum things of the following way. The first term is A1. Well, A1 is really what? It's just the first term evaluated at what I is equal to. Well, I is equal to 1 here. We start at 1. So this is A1 is just 1. A2 is simply the second term of the form of the sum evaluated at the ith term. So the ith term is just 2 because we're just dealing with I. So every time that I move I, I'm just changing the index. So A3 is going to be equal to 3 and so on. So what's really happening here is that I'm just adding the numbers 1, because remember we're summing, 2, 3. What is the fourth term of this form when I is equal to 4? Well, it's just 4 because we're just doing I. What is the fifth term of the form? When I is equal to 5, we just get 5. And when I is equal to 6, we get 6. That is because we simply have I to the first power. So we're simply substituting the values from 1 to 6. So we're going from 1 all the way to 6. We're stopping at 6. And we're plugging in where we see an I. And this sum, if you add it all up, it will be equal to, let's see, so we have 10, 15, 20, 21. Let's see, let me count that again. 10, 20, 21, yeah, 21. Okay, so let's do another one. What if the count now began at 0 and it went up to 5 instead of to 6? And let's say the ith term is given by I plus 1. Well, in this case now, the A1 term is 0 plus 1 because we begin at 0. So 0 will take the value for I, and then we add 1. The A2 term is going to be equal to, well, what comes after 1? After 0 is 1. It's going to be 1 plus 1. The A3 term, the third, remember this is in respect to the terms of the sum. So we began with 0, then 1, now it's 2. So it's going to be 2 plus 1. The fourth term of the sum is going to be 3 plus 1. Again, this is because we began at 0 instead of at 1. So what we really have is the following sum. We have 0 plus 1 plus 1 plus 1 plus 2 plus 1 plus 3 plus 1. Maybe I should erase this from this side. Plus 4 plus 1 plus 5 plus 1. And we stop at 5 because that's the upper bound of the sum. So it's equal to, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, and 5 plus 1 is 6. Notice that this is the same as this, which should tell you that the way in which we write a sum is not unique. This way is completely different to this way, yet they come out, they have the same result. So this is not unique. And we know from the previous problem that it's equal to 21. All right, let's do another one. So what if now we had the sum, this is another popular variable, of j equals 3 to 7 of j squared. Well, now our sum begins at 3 and it goes up to 7. And what are we doing with each j? We're squaring it. So we begin with 3 and we square it. And because it's a sum, we add the next term. The next term is 4 and it's getting squared. Then 5 and it's also getting squared. Then 6. And finally, the last term of the sum is 7 squared. So we get 9 plus 16 plus 25 plus 36 plus 49. And that will be the sum. I mean, if you bother to actually complete the sum, you'll get a solution for sure. But I'm not going to bother completing it. I mean, this is going to be 75 plus 25 is 100, so it will be 125. You can check my arithmetic there. And I did bother to complete it. All right, for the next problem, let's say we have now the following. We have the sum of k equals 1 to n for 1 over n times k squared plus 1. And here's where it gets a little bit, we have to be a little bit clever. So here I'm summing terms, and this is an infinite amount of terms because notice that the upper bound is n, and n could be any value so long as it's not equal to 0, because if you get 0 then this fraction in the front is undefined, but we don't have to worry about 0 because we begin at k equals 1 and we're squaring k. So n could be any value you want except for 0. So what do we have here? Well, since our sum begins at 1, we have 1 over n times 1 squared plus 1. Remember, we're substituting for k values here. Plus 1 over n times 2 squared plus 1. Plus 1 over n times 3 squared plus 1. Plus, and it continues on forever until you get to 1 over n. And what is the last term that you plug in? N. whatever term that is, and you square it and you add 1. So you add all these terms until you get to 1 over n times n squared plus 1. Now, you could simplify this a little bit more, but I'll keep it that way because it will be useful in the future. But you could say that this sum is equal to 1 over n times n squared plus 1. Okay. Well, no, I'm lying. Let me not even go that way, because the n you have to you're adding them, so it will be a bit different when you actually compute all of this. But we can definitely see that the last term is going to be n squared plus 1. Okay, so that's how, and we will be dealing with sums of this form in the next lecture, not in this one. Let's see. And finally, let's do one more, e. So let's say somebody gives you the sum of I equals 1 to n of f of xi times delta x. Well, here the only thing that's changing is the subscript of this xi. So what we have here is simply f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x, all the way up to f of xn times delta x, because the last term in the sum is f of xn. And this is one of the important ones that we will talk. This has a name, and I'll give you that name a little bit later. Now, we definitely will be talking about these Riemann sums, which I just gave you the name, Riemann sum. I'll define what a Riemann sum is. We're definitely going to be talking about summation in the second part of this particular lecture, and I'll define what a Riemann sum is then. But for now, let's talk a little bit about the properties of summation of sigma sums. One of the properties that you should expect is the following, and this is if k is a constant, then the following is true. If you're given the sum from I equals 1 to n of k times ai, then this is the same thing as k times the sum from I equals 1 to n of ai. Okay, because the k is not dependent on the index, you could pull it out. Okay, you could pull it out because it's constant throughout. That's why for this particular problem here, I didn't want to talk too much about it, because I can actually just pull it out because it's just a constant. Well, it's not really a constant, but it behaves like one. But it does change at every single iteration, so that's why you have to be a little careful, because when k is 1, we know what that is, but then we also have to be careful with the n's, because let's say if n is 5, actually, yeah, I could pull it out. Never mind, I could actually pull it out. If n is 5, then it's going to be 5 in all of them. So yeah, we could actually pull it out and have 1 over n times everything, so the answer that I was going to give would have been correct. Anyway, so that's this constant multiple rule here in action. And the other rule that you should expect to work is this one, the sum and difference. So if you have ai plus or minus bi, then that is equal to the sum from I equals 1 to n of ai plus or minus the sum from I equals 1 to n of bi. So you could add sums and subtract sums, or you could just do it on the inside and then separate them. So sometimes it's useful to actually write it in this way, because there are some formulas that become more apparent when you split them up. And that's what I'm going to get to now with the following theorem. So this is a theorem that I'm not going to prove, at least not now, which you have some summation formulas. Now, The majority of these formulas took some time for mathematicians to figure out back in the day, um, but I'm definitely thankful that we have them. Number one is the following: if you have the sum from I equals 1 to n of Cn, actually of C, this is just equal to Cn. And again, that goes back to the constant multiple rule. If you first factor out that C, then you have just a sum of blank. And it turns out that you're just adding this once and many times. So you just get C times n, whatever n is. 2, we have the sum from I equals 1 to n of I. So if you just add regular terms, like if you had the sum from I equals 1 to n of x, then that just means you're adding 1 plus 2 plus 3 plus 4 infinitely many times. It doesn't ever stop. And this is actually equal to n over n plus 1 over 2. I mean, it does stop because we have n up here. So if you add n many terms, this is what they're equal to. The third formula, we have the sum from I equals 1 to n of I squared, and that is equal to n times n plus 1 times 2n plus 1 divided by 6. 2n plus 1 divided by 6. And again, you could derive all of these. The way that you derive them is by literally writing up the sum in this way and finding the sequence of partial sums, which is another sequence that you could create from the terms of the sum, and it allows you to see the pattern. So it allows you to see this pattern right here, like for example n times n plus 1 over 2. Anyway, that's just some information about the proof of this. Finally, the fourth one, I don't know why I'm writing here when I'm going to write it down here. The fourth one is the following: it's the sum from I equals 1 to n of I cubed, and that is equal to n squared times n plus 1 squared divided by 4. And I will not prove any of these, but it is useful that we know them. I will, however, do an example using them, using all of these facts that I have written down. So using this theorem of summation formulas, using these two facts about sums, and using the definition of a sum. So for example, let's say somebody on the train asks you to evaluate the following sum. They told you evaluate the sum it is I equals 1 to n of I plus 1 over n squared for n equals to 10, n equals to 100, 1000, and 10,000. I'm not going to do all of the cases, but I'll definitely do a few of these cases, and I'll leave the rest of the cases up to you. Now, the first thing I will do is just rewrite this. So this is I equals 1 to n. This is supposed to be an I, so this is I plus 1 over n squared. So the first thing that I would do is notice that this n squared is not depending on I. It's not being multiplied by I. There's no i's being added to it. So that means that essentially it is a constant, because when n is 10, n squared is going to be 100 because 10 squared is 100. So it is just a constant that is going to be to multiply, or in this case, you're dividing by it through every term of the sum. So by fact number 1 up here, I can pull it out. I can just take it out. So the same as 1 over n squared times the sum I equals 1 to n of simply I plus 1. But now this second rule kicks in, because we have a sum now. We have the sum of I and the sum of 1. because it's I plus 1. So we could actually split this yet again. So I could write 1 over n squared times the sum I equals 1 to n of I plus the sum I equals 1 to n of 1. And guess what? This is like the first fact that I have up here, because I told you that where is it? Right up here. Because I told you that if we well, this one up here. Because I told you if we factor the c, and this is just cn. In this case, our c is 1, so this is going to be n. If c is 1, then this is going to be n. So we know what this sum is going to be equal to. And we have a formula for this sum, which is right up here. It's n times n plus 1 over 2. So we can apply both of them. So we have 1 over n squared times, again, the sum from 1 to n of I is n times n plus 1 over 2. And the sum of the sum of 1 of I equals 1 to the n of 1 is simply n. Okay? And now what do we have? Well, we have this convoluted mess, and we can combine the fractions on the inside and then multiply through. So that's what I'm going to do. I'm going to combine these two fractions. To combine fractions, the denominators must be the same. So we simply multiply this right fraction by 2 over 2. So we get 2n over 2, and then we can combine them. So we have n squared times n plus 1 plus 2n divided by 2. And then we could multiply throughout. So remember, when you multiply fractions, you multiply across. So this is going to be 1 times the numerator and n squared times the denominator. So what I'm going to do is, as I multiply through, I'm going to actually FOIL this. So it's going to be n squared plus n plus 2n divided by 2n squared. So this is equal to n squared plus 3n divided by 2n squared. Notice that if you factor out an n up from the top, you have n times n plus 3 divided by 2n squared. And so long as n is not equal to 0, you could cancel these. So you get n plus 3 divided by 2n. Because we had two of them in the denominator, we cancel one of them once with the denominator with this one on the outside. So you get n plus 3 divided by 2n. Now we can actually solve the sum for 10, for 100, for 1,000, and for 10,000 by simply substituting in. For example, for n equals 10, we have 10 plus 3 over 2 times 10, which is equal to 13 over 20. Okay. If you have a calculator, you can actually simplify more and turn it into a decimal, but it's not necessary. Let's say for n equals 100, we have 100 plus 3 divided by 2 times 100. So we have that is equal to 103 divided by 200, and so on. So that's why I said, you could do the case for the 10,000 and 1,000. It's not that much difficult. I guess I should show you what it's equal to in decimal form. So let me just do 1,000. This is going to be 1,000 plus 3 divided by 2 times 1,000. This is going to be 1,003 divided by 2,000. And finally, n equals 10,000. It's going to be equal to 10,003. I mean, at this point, you see the pattern divided by 20,000. All right. So what are these equal to in decimal form? If you take out a calculator, you'll see that the first value is going to be 0.65. The second one is going to be, let's see, 0.515. The third one is going to be 0.5015. The fourth one is going to be 0.50015. Notice what's going on. We went with 0.65, then 0.515. then 0.5015, and then 0.50015. So we're getting closer and closer. We're getting closer and closer to 0.50. So notice our values, as n increases, are getting closer and closer to a particular number. In our case, that number seems to be 1/2, because you're getting 0.5. Now, this is true because we can actually find the limit as this approaches infinity. So if, as our expression that we have up here approaches infinity, or goes up to infinity. So let's actually do that. Let's see what that limit is. So if we actually take the limit as n goes to infinity, as n gets very large, of n plus 3 divided by 2n, we get that this is equal to the limit as n goes to infinity. We could actually split this up, so we have n over 2n plus 3 over n. And I mean, we also covered this before with infinite limits. You know that it's going to be a half because they have the same power and the same degree in the numerator and denominator. So it's just the ratio of leading coefficients, so it's going to be 1/2. But just to do the whole limit argument, you can split it up, and then you could take the limit of each term individually. So this is the limit as n goes to infinity of 1 over 2 plus 3 over n, but we know that the limit of this piece is going to 0 because n is getting very big and 3 is remaining constant. So this is going to be 1/2 plus 0, which is just 1/2, because that limit right here is 0. So we see that the limit of this sum, when you take the sum and you look at it as n gets very large, it's going to be 1/2. But we could also see it by looking at certain cases as well. So notice that our sum, we were adding a bunch of infinite things. This is not just a simple function. This is a sum. We're adding things. It turns out that this sum is equal to 1/2. And we're again we're adding infinitely many things, and we're getting that is equal to 1/2. I'm gonna end this part here so it's not too long, and then when we come back, we're gonna be talking about area and the so-called Riemann integral.